Dziękuję za zaproszenie. I'm grateful for your attention here. My name is David Vartanyan. I am a NASA Hubble Fellow at the Carnegie Observatories, where naturally I do theory. And my primary goal here is to motivate capabilities to anticipate the upcoming cornucopia of all-sky multi-messenger observations, particularly or especially for core collapse supernovae. So this is one such explosion we've developed. This is an isoentropy contour colored by electron fraction YE at around half a second after core bounce. The wingspan here is a few thousand kilometers. And this is the early, robust, and very asymmetric explosion of a 25 solar mass model. This work is done with many collaborators, and there's just a few here. But the motivation for this has been over the last decades, with increasing work by many collaborators and many scientists here, to connect with observations. And perhaps the best known supernova remnant is Cassiopeia A, which we have imaged since the 90s. It is now well into its third, fourth century. So we have, in a matter of speaking, almost 400 years of follow-up observations of this one event. And you can see with the launch of James Webb 2 years ago, asymmetries, instabilities, multi-scale structure at every scale of the explosion, including perhaps the environment, the CSM, the circumstellar material, indicated by this well-termed green monster. And you have, in addition to the bubbles, bullets, voids, tangents, filaments, there's an entire vernacular dedicated to describing these structures inherent to the explosion and to its environment, where here off to the center, you see indication of a light echo revealing the asymmetries of the material around the explosion that's reflecting light from the explosion itself. So there are asymmetries at every scales. And we compound this with the fact that we now have a growing library of neutron star and black hole measurements, which can range from under 1.4 to 2 solar masses for the least massive and up to the most massive neutron stars, with a period of a gap between the most massive neutron stars and the least massive black holes, between 2.5, 3 to 5 solar masses, and black holes that are, all of these formed likely from core collapse supernovae, ranging up to perhaps over 100 solar masses. And so if the first seconds of supernova simulation is to hold any water and being able to produce next generation observations, we must be able to reproduce not just the distribution of compact remnants, but also detailed features like the gaps they show. And of course, supernovae are one of the primary channels to drive explosive nucleosynthesis. In Cas A alone, we saw, again, asymmetric structures of alpha elements up to the nickel peak, iron shown here, with a typical energy canonical of 10 to the 51 ergs, and the nickel yield of around a tenth of a solar mass. These are very typical for supernovae, although Cassiopeia A was not a red supergiant explosion, it was a yellow supergiant explosion. And so if our simulations, if our models are to be correct, they must be able to reproduce not just the quantities of these elemental yields, but also the asymmetric structures, like the 3 lobes of iron, which is formed from reactive decay of nickel, seen in Cassiopeia A. And so we show here the early onset of simulations. This is done with our Fornax code. This is, again, the same 25 solar mass model. Again, an entropy isosurface showing the innermost neutron star. I apologize for the lag. It doesn't communicate well with Zoom. But you can see this infalling matter indicated by these blue tracers, large-scale asymmetries on the scale of a few hundred kilometers. And within half a second to a second, the shock explodes. The shock is revived. It launches into an explosion. Within the first seconds, it grows to around the wingspan of a few thousand kilometers. And again, it's a strong explosion. It's very asymmetric. And as I'll show next, it's a very robust explosion, too. And so to quickly summarize where we are as a group, and although I will highlight the work that I've done and contributed over the last several years, this is, of course, relying on a body of collaborations, including many experts here. And so the first problem to try to diagnose was, fine, we can get explosions for perhaps a few models, a growing amount of models, but are they the right energies? And the typical explosion energy should be around 10 to the 51 ergs, or a beta, where an erg is canonically the amount of energy it takes for an ant to do a push-up in Earth's gravity. And so to be able to reproduce these energies, we carry a few simulations out to less than a second. When you get energies that are less than a beta, less than 10 to the 51 ergs, by quite an amount, from a few percent to tens of percent. This is easily resolved by continuing out many models, dozens in 2D, in 3D, hundreds in 2D axisymmetry. And you plot the explosion energies here now for are 2D, and now we also have this for 3D simulations carried out not just to a second, but 5, 6, 7, now getting close to 10 seconds for many of these models. When you said at later times, the explosion energies continue to grow robustly. We have strong energy growth rates, in some cases reaching energies of several beta, but being able to produce low energy, tenth of a beta to 1 beta canonical explosion energies, like we infer from CAS A. So we can get the correct energies, and we can then overplot this with observed energies. Black are our simulation energies against ejecta mass, energy on the y-axis, and these colored points with error bars are for observed type 2p energies from observed supernovae. And we can reproduce the trends quite well. It's not perfect, it's not meant to be perfect. We can reproduce the general trends without any matching of simulations to the observations. These are very asymmetric, and they can leave behind remnants that can be up to 2 solar masses for neutron stars, more massive for black holes, but perhaps for some intermediate cases, they're now carried out from seconds out to days, even weeks for some models. We can reproduce perhaps, in rare cases, candidates leave behind the remnants in this mass gap location between around 3 to 5 solar masses. So late time fallback accretion of the outer mantle and perhaps the envelope can trigger events that may lie in this observed mass gap. We can also leave behind kicks for low mass, low explosion energy neutron star explosions with around the few tens to 100 kilometers per second, up to the most energetic cases, leaving behind the kicks in some cases of black holes above 1,000 kilometers per second. And we find the interesting phenomenon that you can get joint formation of an explosion that later has an energy around the beta, that later has sufficient fallback and leaves behind a black hole. So you can get joint formation of a black hole with a large kick and the robust explosion with energies above a beta. And we get yields. We now plot the yields, the mass fraction of, the amount of nickel formed in solar masses as a function of explosion energy. And we're able to produce 10 to the 51 ergs of energy for a CAS-A-like event with around a tenth of a solar mass of nickel, as we inferred from CAS-A observations. And so carrying out these simulations with the simple inclusion of complex neutron physics, none of this uses rotation, none of this invokes magnetic fields, we can begin to reproduce a litany of early features that correspond with observations. Simply by continuing these simulations out to late time, seconds, now out even later, with the detailed 3D neutron capabilities. And a quick aside, this is a 40 solar mass model that, as I mentioned before, both explodes robustly and then accretes in the first seconds through infall accretion. It's a massive progenitor to trigger formation of a black hole. This is a solar metallicity progenitor. And at late times, in the first 2 seconds, we see a neutrino-driven jet-like feature when viewed off-axis also shows a low entropy disk-like feature and is kicked with the remnant kicked opposite to the ejecta distribution with velocities of above 1,000 kilometers per second. In some cases, neutron stars, and in this case a black hole, can have significant spins. This has a spin alpha of around 0.5. We can infer neutron kick spins from initially non-rotating models through some sort of coherent advection of material that drives rotation in the core down to tens of milliseconds and as slow as out to seconds. So we can produce millisecond-like neutron stars without invoking any initial rotation, again through 3D late-time neutron-driven simulations. And so we can then go and try to take on this multi-messenger dynamic in more rigor. And first, I'll show you a distribution of gravitational waves. Bernard also already did a great job motivating this. So I'll just show on the left column, I show spectrograms of failed explosions. On the right column for successful supernovae. And this top row here is an energy spectrogram in gravitational waves, and the bottom is a strain spectrogram. And so you can see multi-scale features encoded in the gravitational waves. For failed models, we see in the strain a spiral Sassy-like feature that is manifest. We don't see this for successful explosions unless it's a very rare case that explodes lately. We can see this high-frequency component in all models. We identify this as an F mode. In successful explosions, we see this early high-frequency feature, which we correlate strongly with the turbulent accretion of matter that rings onto the PNS. And at later times, for exploding models, you see this offset at low frequencies, lower than the Sassy, but only for explosions, which is due to the matter memory. There's a large-scale ejecta that drives a low-frequency, but perhaps high-amplitude signature visible in successful explosions. I show here, just to be comprehensive, strains from matter contributions, but you also have contributions to gravitational waves from neutrino asymmetries, which carry a large lever arm. There's a lot of energy present in the neutrino component of explosions, but with a smaller asymmetry. So you have much higher strains because the neutrino luminosity is integrated. So you have this cumulative semi-monotonic growth out to very high strains, reaching above 1,000 in h times d in centimeters in the first tens of seconds, whereas the matter contribution is at much lower strains. You see a prompt convection early on, this turbulent accretion, and then a memory offset later time, which can be several centimeters. Much higher strains in the initial contributions, but much lower frequencies, which translates directly to much lower energies in the gravitational waves released from neutrinos, a few orders of magnitude lower than that released in matter. We show here in these black and blue curves the gravitational waves from matter in the first, again, 4 or 5 seconds, and we overplot in blue the turbulent hydrodynamic luminosity, and we see a strong correlation in the accretion component, which is driving this turbulent luminosity around the neutron star that rings the neutron star, with high entropy plumes probing like fingers and exciting the neutron star in the center. And so we see strong evidence that turbulent accretion is powering the dominant source of gravitational waves in the first seconds. In recent work with an undergraduate, Lila Choi, was at Princeton, now is starting a graduate program in Stanford. We did this in more detail. We developed, as Thomas showed earlier, now frequencies against the sensitivity of different instruments, including the Einstein Telescope, Cosmic Explorer, DESIGO, Advanced LIGO, and here in this black curve, the sensitivity of the lunar gravitational wave antenna, LGWA, which will be launched, well, hopefully launched in the next decades on the moon, where there is less noise from us walking and driving cars. And we show here for models from 9 to 60 solar masses the sensitivities we expect to see in these noisier colored plots, and many of them lie above current and next generation detectors. And so if a supernova goes off in the Milky Way, we're at least poised to see it for a 10 kiloparsec event across all mass ranges we considered. And perhaps you can probe lower frequency components like matter memories and neutrino memories with instruments like DESIGO and LGWA. That's what the signature sounds like for a non-rotating supernova. It is in the kilohertz bandpass, so it's audible to the human ear. Enough for a rotating supernova where you hear a distinct chirp due to the prolate oblate oscillation of the neutron star in the very first milliseconds of core bounce. Going forward now to neutrinos, if we're fortunate enough with collaborations like SNOOS and CWB, the current wave background, to get joint detection of these rare events in both neutrinos and gravitational waves, we'll be able to say so much more about the otherwise opaque core properties. We see strong correlation between neutrino energy, here plotted on the x-axis, and the compactness of the core defined as the mass and the radius of the innermost core, how dense the core is. More compact cores, hotter colors, liberate more energies in neutrinos and leave behind more compact neutron stars. The compactness is not a metric of explodability, but it is a measure of how many neutrinos you produce and what your accretion rate is. And if you also then repeat this analysis for gravitational waves with our 3D models, we see that more compact cores liberate more energy in gravitational waves. And if we're able to get joint detection, we plot here in Lila Choi's paper the gravitational wave spectrogram in this color plot on the back, and this red line shows the cumulative loss of neutrino energies in the first seconds. And you see that this loss of neutrino energies correlates very strongly with the dominant F mode of turbulent accretion-driven gravitational waves. We then also see that when we plot the neutrino luminosities versus time, that models that are more compact, have more compact cores, have a longer lasting plateau phase in the neutrino luminosity. The luminosity rises, falls at breakout, plateaus, and we see a tail. And we can see this weak correlation with the time of the plateau, the duration of the plateau, and the core compactness. So this is sort of a Phillips-like relationship, but for core collapse supernovae, not type 1As, and for neutrinos and not for light. And so we remain optimistic, hopeful for a perhaps near future detection of gravitational waves and neutrinos. But at the same time, we are sitting on a gold mine or a landmine, depending on your perspective, of observational data, light curves, spectra, In the last 20 years, with Hubble and the Carnegie supernovae and the SDSS, we had less than 1,000, around 800 supernovae detections. With the launch of ZTF, Pan-STARRS, Atlas, SAS, and many others, this then grew out to thousands. With the hopeful launch of LSST in the next several years, this will grow super exponentially to produce a catalog of millions of core collapsed supernovae over the next decade. But from a theoretical perspective, we now rescale the plot. We've had a handful of simulations as a collective audience in the last decade. Perhaps this has grown now increasingly in the last years, but it still dwarfs what observation capabilities can provide. So how can we bridge this gap between theory, which only recently has been able, through collaborations like this, produce early explosions, with the absolute onslaught of observations we expect to see? And so to really turn this pipe dream into a pipeline, we, including a collaboration with Lizzie Teroshin, a former undergraduate I work with, developed this comprehensive study that's meant to be modular, where we anticipate evolving from the final stages of stellar evolution out through the first seconds of a neutron-driven explosion, out to the propagation of the shock until it reaches the stellar surface, and beyond it, where we can get early light curve spectra, modeling from bound to beyond the breakout. And I want to highlight some early observations. This was published in a paper last year. We have a follow-up coming up in the next month, where I show on this left column observations, on the right are simulations. So we've seen for CAS A heavy mixing of nickel, shown in blue, with oxygen, shown in red, out to very late times, centuries. For our models, we can see that this vermiform structure of oxygen is punctured by nickel eject that's moving at higher velocities. When overplot, you can see the structure here. We see heavy mixing of nickel that's ballistically formed through explosive burning and is mixed heavily beyond the oxygen, which lies exterior to it initially. We see in delay in 2010 this strong feature of the reverse shock, this almost pristine sphere, which can reproduce in the first months as you follow the ionization fraction of our simulations beyond shock breakout, from seconds to eventually, hopefully, centuries. And perhaps even more interestingly, we can see we have observed these silicon rings and iron crowns. We have ring-like features in Cassiopeia A, punctured by nickel bullets to form this crown-like feature. And you can see similar features that are observed in our simulations. We see these blue silicon rings punctuated by these red nickel bullets. I want to play an illustration of how such a bullet develops. You can see that nickel is mixed outward as it reaches this hydrogen-helium envelope, which triggers a reverse shock. The reverse shock propagates inward, seeding radiational instabilities, which then punctuate nickel into the outer envelope. And we carry this out to later times. This is now at shock breakout. This is now going to evolve past shock breakout into a low-density environment. We can see these initially small-scale nickel features form large-scale bullets, which are on size scales that are characteristic of the entire size of the explosion. So you see these large nickel bullets form in situ just by carrying these emissions out to late times, their first days to weeks. Now I show here an evolution of the entropy out to these first days. You see the shock propagating outward. This is a low mass, non-star mass explosion, but even this evinces some large scale asymmetry. There is a delay in shock breakout by viewing angle. That's a reverse shock propagating inward. It reflects off center. The shock breaks out, and it is heavily mixed material closely following the shock front. And so we can reproduce CAS A-like events where you can get a beta of energy, a tenth of a solar mass of nickel, but we still have to try to reproduce these features we've seen in iron, which is a decay product of nickel. In particular, we saw these three lobes in CAS A. Now, for one of our models, we are able to reproduce the stochastic development of perturbations in nickel that can then propagate outward and form radiational instabilities into nickel boats. These same three plumes in nickel that will then decay into iron. This is a 23 solar mass. Well, we're not trying to match observations. The goal here, the conclusion here is that doing these simulations at scale, out to late times, provides generically results that can comport strongly with observed features across a diverse spectrum of observations. And we also have the first templates. I show here light curves developed with Dan Case and now with David Katami. The colors here indicate different lines of sight, different viewing angles, and we see significant variation in the first 2 weeks in the plateau out to the decay tail in luminosity by viewing angle. And then we're able to map the nickel velocities at breakout for different models. We now have half a dozen going on to a dozen models carried out to shock breakout. And we see that this clumping of nickel is manifest in this histogram in velocity space. And this will imprint onto the ejecta, which will be visible in the first months. Once the explosion cools, the photosphere recedes, and you see the asymmetries just anterior to it. We can also reproduce early spectra. This is an angle average spectra for a low energy explosion in black, and the different angle varying angle variations, and this gray line behind it. Just for our own interest, we compare this to supernova 2005 CS. This red line is an observed spectra of a supernova 2005 CS, and you can reproduce some, but not all of the features without intending to match any of the properties of the progenitor. And I'm happy to talk about why we can succeed and where we fail in this comparison. But you can now reproduce, you can begin to produce light curve spectra and hopefully reproduce observations from first principle simulations. And what does this mean for the observing community? Historically, we've relied on 1D models of shock explosion with different parameterizations carried out with 1D light curves that we show here. The shock breaks out, it's a stately peak, and it falls. Now, if you do this in 2D, because the breakout is so asymmetric, it breaks out along different directions at different times, this peak is then stretched out over several days. And so instruments like ultrasat, which will sample the sky at a cadence of 90 minutes with large viewing angles, will be able to capture the fall of this breakout, a peak with a greater probability because it is stretched out to many days and not just a few hours. And this is work done with David Katami in preparation, where we now do this in 3D. So this is a 1D breakout, like I showed earlier, but now in 3D along different lines of sight. You can see how the breakout time is smeared out over several days. And this is manifest in the light curve observations. And this is really a problem because there are already great uncertainties in extrapolating explosion energies and masses there are errors of orders tens of % from observations of light curves and later for spectra. And if you then go to 3D, the variation increases even more. And this is now the first, as far as I know, the first 3D intensity map of a simulation where we see the early breakout, and now we see this cratering as metal ejecta leaves the shock and breaks out into it. And we see these large-scale clumps observed in the first days, in the first 60 hours. And so developing in 3D light curves and 3D intensity maps of shock breakout illustrate the inherent intrinsic multi-scale structure that is set in the first seconds by neutron-driven explosion. I'll skip, how am I doing on time? Okay. 8 minutes. Okay, so then quickly go through these results. This is mentioned before by Bernard, and I think it's been well appreciated for the last 20 years, that the structure of the progenitor imprints onto the properties of explosion. And so we've seen that models that have a strong silicon-oxygen interface, in this bottom left circle in this dotted ellipse, where the density drops by a factor of several deep inside the stellar core, are more likely to explode, all else being equal. You have a high density interior to the interface that powers a high accretion neutrino luminosity, and then almost immediately the density drops, the ramp pressure drops, and so you have a shock powered by a high neutrino luminosity facing a region of low ramp pressure at the silicon-oxygen interface. This, all else being equal, promotes explosion. And we find that models with a strong interface, these solid lines, explode or exploded earlier than those without an interface. You can then parameterize this. And we've done this analysis for, you can determine by eye if a star will explode ab initio. If it has a strong interface, you can conclude that it will likely explode. You can do this analytically or semi-analytically. You can even do this with the machine learning techniques. We characterized explosion outcome with 2 parameters for trained on 100 models, where the interface is in mass and how steep is the density drop at the silicon-oxygen interface, which is coincidentally found just outside the iron core. So it's encountered early on by the expanding shock. And we found with around 90% accuracy that a strong silicon-oxygen interface, parameterized by these 2 features, can predict explosion outcome. So you can get some of the fidelity of these multi-scale complex red hydra simulations with a simple machine learning approach that can predict quite well whether the model will explode or not. There are limitations as to why it's not going to be 100%. It will never be 100%. Supernovae are not two-parameter. They're not two-parameter physics phenomena, but this is still quite robust. And I'll just briefly say that neutrino microphysics also matter, inclusion of detailed physics like many-body correction through the scattering rate, which will decrease the scattering cross-section, promote a greater neutrino loss from the core. The core will shrink, heat up, produce more energetic neutrinos, so then couple back in and increase the neutrino matter cross-section just outside the core and increase the shock radius's likelihood of expansion are key. And by no means are any of the simulations done to date completely comprehensive in their body of neutrino microphysics, and there's absolutely still work to be done here. I do also want to say as an added caveat that there is a whole body of uncertainties. The nuclear equation of state, which can be probed by joint measurements of gravitational waves and neutrinos, is incredibly uncertain. In 2017, Jim Latimer and his students published a paper that effectively ruled out, using an approximate unitary approach, half of the nuclear equations of state used in the supernova context. Recent experiments done with the Jefferson Laboratory ruled out the remaining other half of equations of state in the supernova context. And so surviving equations of state that can robustly model the supernova phenomena are tenuous to find and defend. Secondly, much of the uncertainties we see, and Bernard also mentioned earlier, we have this red supergiant problem. We are in many ways held hostage to uncertainties in the progenitor of these massive stars. And so having improvements going into 3D with better approximations, treatments of convection pre-collapse, with better treatments of mixing of convective overshooting, of the uncertainties in nuclear burning reaction rates are incredibly important to better model the initial conditions, which, as you saw earlier, are so key to determining explosion outcome. And so with those uncertainties in mind, I want to just leave you with some concluding remarks that when Euclidean models out to shock breakout, we see the preservation of asymmetry at all scales, at all phases, and we see heavy mixing of metals that are produced largely in explosive burning out through the stellar envelope. And these will manifest in the spectra of observations. We see that these late time structures on the left, shown at a couple of days, on the right, a couple of days, on the left at a few seconds, the dipolar structure is imprinted from the first seconds for many of these models, and perhaps it wrinkles a little bit more as instabilities develop. Also, 1D models for light curves built on a 1D approaches to supernova simulations are now, they have been incredibly useful to date, but they are now, we find, incorrect and also perhaps misleading. I do want to emphasize that we can generically begin to reproduce observations with our simulations. One interesting find was that in 87A, there was this detection of the Bolcom event, where in the first 20 days of follow-up observation in light, there was evidence for strong mixing of nickel into the hydrogen envelope, where the estimates were you had around 1,000th of a solar mass of nickel mixed with velocities of around 4,000 kilometers per second. For our 17th solar mass model, which explodes around the beta of energy, this is not a blue supergiant. It's not like 87A, but we find that within the first days, we have 1,000th of a solar mass of nickel mixed into the hydrogen envelope, moving at around 4,000 kilometers per second. So these in-situ simulations are able to reproduce generic observations across a whole spectrum. And I want to come to a final conclusion with a bit of levity. You may be familiar with Maslow's hierarchy of needs, which says that to reach self-fulfillment, we must first have our physical needs, food, water, shelter, then our psychological needs met. I want to introduce a similar hierarchy, yet unnamed, for supernova theory. For over a decade, we have struggled to get explosions, but now with communal efforts, we can now begin to ascend this narrative arc and forge a more intimate connection between the theory of today and the observations of tomorrow. Thank you.
Okay, thank you, David. We have time for a few quick questions, so maybe start over here. Thank you.
Thank you, David, for the talk. You have shown the impact of the progenitor structure on the final outcome of the explosion. And I noticed that the density profile is not monotonic with the initial mass. Has this some consequence on the outcome? Probably you already mentioned it, but probably I missed this point.
Yeah, no, absolutely. I did not mention that. It's a very good point. There is no monotonic dependence of explosion outcome with the mass of the progenitor. If you can at all trust these masses, these are developed at 1D models. We don't know if there's a canonical 15th solar mass in nature and what that looks like. But all simulations to date have shown no monotonic dependence with the progenitor mass. Perhaps lower mass models, if they explode, will explode with less energy. Higher mass models, if they explode, will explode with more energy. Yeah. But there is no monotonic dependence because the density is not a simple function of the progenitor mass, but there's robust correlations regardless.
Okay, but can you explain such a non-monotonicity with the initial mass of the density structure? Why the density structure is not monotonic with the initial mass?
Right. So generally you can see that as you go to higher masses, you have smaller core densities. This is just a function of stellar theory, stellar evolution theory. But there are uncertainties here, and
Yeah.
the models we use from Kepler embody some of these uncertainties. For instance, between around 15 to 18 solar masses, you have transitions from radioactive convective and nuclear core burning. You have shell mergers that can emerge. So there's inherent stochasticity in the evolution of these massive stars. But also, as you go to more massive stars, you expect to see these more massive tails, a higher density of tails at larger masses. So there's still some trend here that's a function of progenitor mass, but it is not monotonic.
Okay, that was a long question, so we don't have time for many more. Let's thank the speaker again and move on to our last speaker.